In this video, we're going to go through an example of sort of an application of biaxial bending with a rectangular cross-section. So what we have here is a 2-meter long cantilever, and it's a rectangular cross-section which is 100 millimeters wide by 300 millimeters deep, but it's canted over at a 45-degree angle, and it has a point load on the top corner of 5 kilonewton meters. And so what we want to do is find out what the bending distribution is on this. And so, one of the first things we can find is that our maximum moment is simply going to be 10 kilonewton meters. And then, so if we sort of draw our cross section here, now one thing that we do know is because we're working with a symmetric section, our centroidal axes, sort of conventional X and Y, are also going to be axes, also going to be the principal axes. And so what we can do is set up effectively if our sort of resultant bending moment is at 45 degrees of 10 kilonewton meters, we know that we've got a moment, mx equal to, it's going to be cosine of 45 degrees times m, and in my equals sine of 45 degrees times m, and this is going to be 7.07 kilonewton meters, and again 7.07 kilonewton meters. So again, all we're doing is we're just taking this resultant moment and breaking it out into its components. And now this is a problem which we've seen before, where we have a cross-section which has principal axis, has bending about both of them. And so in order to determine what our bending stress is, we can just use superposition, where our stress is simply going to equal m times v over iu plus m times u over iv. And of course this will be bending about the x and bending about the y. So, very similar to what we do for a Cartesian coordinate system, where we're just going to add the two up. I guess the first thing we want to know is that, because I and u are going to be equal to the same, and also that I've got my axes oriented in this direction, just mostly so that we're consistent with the y being down from the neutral axis, like how we derived our bending stress, but it doesn't really matter as long as you're consistent. So for we need to know these two. We have our, so this for I of u, this would be mu and mv. All right, so we know mx is going to be equal to, so mu equals mx equals 7.07 kilonewton meters, and mv equals my equals 7.07 kilonewton meters. So we know mu, know mv. We need to work out what iu and iv is. So there's simply just going to be the moments of inertia about those given axes. So pretty straightforward since it's a rectangle. We've done this before. Iu is going to be 1 over 12 times the base, 100, times the height cubed. So iu is equal to 225 times 10 to the 6th millimeters to the 4th. And iv, 1 over 12 times 300 times 100 cubed. iv equals 25 times 10 to the 6th millimeters to the 4th. Well, now we have kind of all of our pieces, and as we sort of looked at in our, our derivation of how do we work out biaxial bending, let's just take our points of interest, so, the corners effectively, and work out what the stress is in each of these, and we just have to make sure that we stay consistent with our cross section, and also sort of what our moments would be there. So both of these moments are sort of let's say negative moments, if you would, just based upon the direction in which they're going. And so in fact we can just say that this would be a negative and a negative, which again we're going to put the top into tension. All right, so here we go. Sigma A equals negative 7.07 times the distance V up, which will just be minus 150, since we're Y is pointing down, times 1,000 times 1,000 to get us into, so this is in newtons per kilonewton, millimeters per meter, over 225 times 10 to the 6th, plus negative 7.07 times negative 50, because we're going over 50, times 1,000 times 1,000 over 25 times 10 to the 6th. And what we end up with is sigma A equals 4.7 MPa minus 14.14 MPa. Sigma A equals negative 9.44 megapascals. All right, simple enough. Again, just sort of kind of keeping track of what we've got going on here. Sigma B. So our stress at point B. So we know that these are going to both sort of stack up. We know D is going to be in compression, A is going to be in sort of tension there. So we would get minus 7.07 kilonewton meters times, so I apologize here. I think I wrote the wrong bit. This is a positive 50. Obviously we're going over 50. Sorry, I made a small mistake there, so apologies, which is why we end up with a negative instead of a positive. So but again, to fix that, and again this is sort of maybe brings up the point, just make sure that you do have to sort of keep track of where you are. As you can see, it's pretty easy to make a mistake, so it's always good to just sort of go back and double check and make sure that things do make sense. But for B, we know we're going to go minus 50 and minus 150 for our coordinates of x and y. So we'd have minus 707 minus 150 times 1,000 squared to get us into the correct units, over 225 times 10 to the 6th millimeters to the 4th, plus negative 7.07 times negative 50 times 1,000 squared over 25 times 10 to the 6th. And again, all we're doing here is just simply plugging and checking our moments and our coordinate systems. This will end up giving us sigma B equals 4.7 MPa plus 14.14 MPa. Sigma B equals 18.84 megapascals. Sigma C, so now we're coming down to this point here. It's simply going to be, our x and y will be a positive 150 down and a positive 50 over. So we have negative 7.07 kilonewton meters times 150 times 1,000 squared over 225 times 10 to the 6th plus minus 7.07 times 50 times 1,000 squared over 25 times 10 to the 6th. And if we get that, we find we've got minus 4.7 MPa plus minus 14.14 MPa. And that's going to mean that sigma C equals minus 18.84 MPa. So that's a compression force there. And then finally at sigma D, we're much the same, but we've come with a positive y and a negative x coordinate. So minus 7.07 kilonewton meters times 150 times 1,000 squared over 225 times 10 to the 6th plus negative 7.07 times negative 50 times 1,000 squared over 25 times 10 to the 6th. And we find sigma D equal to 9.44 megapascals. So let's go ahead and kind of plot what the stress distribution would look like as a cross section. So we've got A, B, C, and D. Sigma B equals 18.84 megapascals. Sigma D equals 9.44 megapascals. C is negative 18.84 MPa, and A is negative 9.44 MPa. And again, negative we're saying is compression, and positive is tension. And so there'll be some, neutral axis coming through about like this. So this is our compression side, and this is our tension side. So because we are going to be so dependent upon our sign conventions and making sure we're right, this is always where it's useful to make sure, well, if based upon the direction of the bending moment, we should be able to work out, what side's going to be our maximum compression, what side's going to be our maximum tension. And we can always use that to sort of double check ourselves and make sure that we did get our sign conventions right. So if we've got our moments here, again, point our thumb in the direction. So we're bending this way and we're bending this way. So we know that C is going to be our maximum compression and B is going to be our maximum tension. And so if we're finding, as you can see, everything's kind of symmetric here. So if we're finding that we have, say, we know if B is going to be our maximum tension, and we're finding that we're getting a compression force or it's not the maximum, well, we know we've messed up our sign notation there. So as I said, it's always a little bit tricky to make sure we stay consistent with our sign conventions. But by just sort of looking at what the structure is going to do, well, we know the top is going to be in tension, and we know the bottom is going to be in compression. So, if this is effectively, B, A, C, and D, well, that helps us make sure that we're working out the right orientations. Now, I guess the only thing we have to work out is sort of, what our angle alpha is of our neutral axes. And so in order to do that, well, we got sort of two ways to look at it. We can either look and see when our stress is equal to 0, so when this effectively my over I in both directions is equal to 0, and then work out sort of what the slope of the line is. Or we can sort of take it from the fact that we know that our load is applied at a 45-degree angle, call this theta, and then use our relationship between our 2-second moment areas to get us there. So we're going to do it both ways and just sort of see the difference. So go find angle of the neutral axis. And so we'll have stress equals 0 equals mu v over iu plus m v u over I v. So 0 equals negative 7.07 times 1,000 squared times v over 225 times 10 to the 6th plus negative 7.07 times 1,000 squared times u over 25 times 10 to the 6th. If we simplify this, then what we end up is 0 equals 0. Negative 0.0314 v plus negative 0.283 u. And then if we work out sort of our v, do a little bit of rearranging, v equals 0.283 over 0.0314. And then we end up with, let's just calculate that real quick. .283, we get times u. V equals 9.13 times u. And so we know that tangent of alpha equals v over u. Alpha equals the arctangent v over u. Alpha equals tangent negative 1 of 9.13. And so alpha equals 83.7 degrees to u axis. So that's one way to find it. And again, alternatively, we can just sort of use our ratios of our moments of inertia and the fact of the applied angle, which is really just doing the same thing, but just taking the fact that, if we already know what the applied angle is, these are effectively the components of it, which are, broken down based upon that angle. And so I just want to show you that it's sort of giving you the same answer. So alternatively, use the fact that the load is applied 45 degrees equal theta to the principal axes. And therefore, tan of alpha equals IU over IV tangent of theta equals 225 times 10 to the 6th over 25 times 10 to the 6th times the tangent of 45, and we get alpha equals 83.6 degrees. So almost exactly the same. Some slight rounding errors, obviously, with cosine of 45 degrees, not quite 7.07, so, but pretty close. And again, it's really just the fact that this tan of 45 degrees is just accounting for the ratio of our mu to mv anyway, so it's effectively doing the same thing. So I hope you found that example, again, reasonably straightforward. As I said, it's mostly just a bunch of bookkeeping. There's nothing that you really haven't seen before if we're working with principal axes. It's just making sure that your bending stress is going in the right direction. And as I said, so it's something that I always get confused on, I always find challenging. And the only way I can sort of work my way around it is I look and see, well, if I've got a bending here, I know that B is going to be my maximum tension and C is going to be my maximum compression, just from what the structure is doing. And so I can use that to double check and make sure I've got the correct sign on my moments, the correct sign for my coordinate system. And because without that, I find it personally quite confusing, and I'm sure many of you will find it the same. So again, the big trick on this one is just make sure that you think about what's actually getting bent around the structure, and don't just blindly apply these equations. And then you should always be quite fine there. And again, the sort of last trick in terms of finding the angle of the neutral axis is just working out when your bending stress is equal to 0, and it's just the angle that that line makes. So with that, we're going to wrap up there, and I hope you found this helpful and a sort of, hopefully pretty straightforward example on how to apply biaxial bending stress. All right, with that, thanks for watching.